Here's the thing about Earth. Every 100,000 years, like clockwork, the planet freezes. Ice spreads from the poles. Glaciers march across continents. Sea levels drop hundreds of feet. Entire ecosystems shift toward the equator. Then, just as predictably, the ice retreats. The planet warms. Life spreads back north and south. This has happened over and over for millions of years. The pattern is so regular, you could almost set your watch by it. Almost. Because here's what makes this truly strange. The cycle isn't quite perfect. It's close. Incredibly close. But there are wobbles, variations. Times when the ice should have advanced, but didn't. Times when it should have retreated, but lingered. And nobody knows exactly why. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always check the comments, and it's fascinating. We know the ice ages happen. We can measure them in ice cores drilled from Antarctica, in ocean sediments pulled from the deep sea floor, in the rocks scraped and carved by ancient glaciers. The evidence is everywhere. We even know some of the reasons. Earth's orbit changes shape. The planet wobbles on its axis. The tilt shifts slightly. These changes affect how much sunlight hits different parts of the planet. They create cycles, predictable patterns in the amount of solar energy reaching Earth. But here's the problem. Those orbital changes alone aren't enough. The math doesn't quite work. The wobbles in Earth's orbit should create temperature changes of maybe 1 or 2 degrees. Instead, we get ice ages. Full glacial periods where ice sheets cover half of North America, where the climate shifts so dramatically that entire species go extinct or evolve or migrate thousands of miles. Something is amplifying the signal, taking those small orbital nudges and turning them into massive climate swings. Scientists have been trying to solve this puzzle for over a century. They've proposed dozens of theories, some elegant, some bizarre, some that seemed perfect until new evidence proved them wrong. The answer, it turns out, involves everything. The oceans, the atmosphere, the ice itself. Carbon dioxide locked in rocks and released by volcanoes. Dust blown from deserts. Plankton in the sea. Forests spreading and retreating. All of it connected in ways we're still figuring out. And the really unsettling part? We're living in one of the warm periods right now, between ice ages. The ice will come back. Maybe in 10,000 years, maybe in 50,000. This cycle isn't done. Unless we've broken it, which is a whole different question. Chapter 1. The discovery of ice ages. The first person to really understand that ice ages happened wasn't a scientist. He was a Swiss carpenter and hunter named Jean-Pierre Perraudin. The year was 1815. Perraudin spent his days in the Alps guiding travelers through mountain passes. He noticed something strange. Huge boulders sat in the middle of valleys, miles from any cliff they could have fallen from. The rocks didn't match the stone around them. They were granite, but the valleys were limestone. Perraudin had a theory. The glaciers had carried them. He told this to a Swiss engineer named Ignaz Venitz. Venitz laughed. Everyone laughed. Glaciers moved slowly, maybe a few feet per year. How could they possibly carry boulders the size of houses across entire valleys? But Perraudin was persistent. He showed Venitz the scratches, long grooves carved into solid rock, all pointing the same direction, down from the mountains. Venitz started paying attention. He looked at the boulders again. He measured the scratches. He talked to other mountain people. They all said the same thing. The glaciers used to be much bigger. You could see where they'd been. The evidence was everywhere. Venitz became convinced. He presented his findings to the Swiss Society of Natural Sciences in 1821. Most scientists dismissed him, but a few listened. One was a young geologist named Louis Agassiz. Agassiz was skeptical at first. He went to the Alps to prove Venitz wrong. He spent the summer of 1836 studying glaciers. measuring them, watching how they moved, looking at the rocks they carried. He came back convinced that Venice was right. More than right. The glaciers hadn't just been bigger. They'd covered most of Europe, all of Scandinavia, much of Britain, parts of Germany, and France and Switzerland. Agassiz called it the Ice Age, Eichheit in German. He presented his theory in 1837. The scientific community was not impressed. The problem was the dominant theory of the time, catastrophism, the idea that Earth's features were shaped by sudden, violent events. Most geologists believed in the biblical flood. They thought the boulders had been carried by rushing water. The scratches were from debris in the floodwaters. Everything could be explained by one great deluge. Agassiz was proposing something different. Slow change, gradual processes, ice advancing over thousands of years. It contradicted the prevailing view, but Agassiz had evidence. He showed colleagues the polished bedrock, the parallel scratches, the U-shaped valleys carved by ice, the moraines, long ridges of debris left when glaciers retreated. You couldn't explain all of this with a flood. Slowly, scientists started to accept it. Charles Lyell, the most influential geologist of the era, was convinced by 1840. He saw the evidence in Scotland. Scratched rocks, erratic boulders, glacial valleys. It all fit. By 1850, the Ice Age theory was mainstream. But scientists thought there had been only one ice age, one period when glaciers covered the northern continents. Then they melted. End of story. A next discovery changed everything. In the 1860s, geologists started finding multiple layers of glacial deposits. In some places, there were clear boundaries, old glacial debris, and a layer of soil and plant remains, then more glacial debris, then another soil layer, then more ice deposits. Each layer represented a different climate. Glacial periods separated by warm periods. There hadn't been one ice age. There had been many. James Geikie, a Scottish geologist, documented this in detail. He identified at least 4 separate glacial periods in Scotland, each separated by warmer interglacial periods when plants grew and soils formed. The evidence kept mounting. In the Alps, geologists found the same pattern. Multiple glacial advances, each one pushing rock and debris downhill, each retreat leaving behind distinct deposits. In North America, the evidence was even clearer. The Great Lakes region showed layer after layer of glacial till, different ice sheets at different times, some reaching as far south as Missouri, others stopping in Wisconsin or Minnesota. But how could anyone prove this? How could you date rocks that were hundreds of thousands of years old? Radiocarbon dating wouldn't be invented until the 1940s, and it only worked on organic material less than 50,000 years old. The breakthrough came from an unexpected place, the ocean floor. In the 1950s, oceanographers started drilling cores from the deep sea, long cylinders of sediment pulled up from the bottom of the ocean. These cores contained the shells of tiny organisms called foraminifera, forams for short. Forams are single-celled creatures. They build shells from calcium carbonate. When they die, the shells sink to the ocean floor, layer after layer, year after year, for millions of years. Here's what made them useful. The shells contain oxygen, specifically oxygen isotopes, oxygen-16 and oxygen-18. The ratio between these two isotopes depends on temperature. When the world is cold and ice sheets are growing, more oxygen-16 gets locked up in ice. That leaves more oxygen-18 in the ocean. Forams building shells during ice ages incorporate more oxygen-18. When the ice melts, the ratio shifts back. Scientists could measure these ratios. They could see the ice ages in the foram shells. Each layer of sediment represented a different time period. You could read climate history like a book. Cesare Emiliani did exactly this in 1955. He analyzed foram shells from Caribbean sediment cores. He found a clear pattern. Warm periods and cold periods alternating over and over, going back hundreds of thousands of years. He identified what he called oxygen isotope stages. Odd numbers for warm periods, even numbers for cold periods. Stage 1 is now, our current warm period. Stage 2 was the last ice age. Stage 3 was a cooler period before that, and so on. The pattern was remarkable. The ice ages weren't random. They followed a rhythm, a cycle. Roughly 100,000 years between major glacial periods, with smaller variations in between. Other scientists confirmed this. They drilled cores from different oceans: the Atlantic, the Pacific, the Indian Ocean. Everywhere they looked, they found the same pattern, the same cycles, the same rhythm of ice ages. Then came the ice cores. In the 1960s, scientists started drilling into the ice sheets of Greenland and Antarctica. These weren't like ocean cores. Ice cores contained actual ancient atmosphere, tiny bubbles of air trapped when the snow fell and compressed into ice. You could measure the carbon dioxide in those bubbles, the methane, the temperature when the snow fell. You could see volcanic eruptions as layers of ash. You could count the annual layers like tree rings. The first deep ice core came from Camp Century in Greenland. Drilled between 1963 and 1966, it reached bedrock at 4,560 feet. It contained ice over 100,000 years old. The data confirmed what the ocean cores showed: regular cycles of warming and cooling. Ice ages followed by warm periods, over and over. But the ice cores revealed something the ocean cores couldn't: the speed of change. Some transitions from ice age to warm period happened incredibly fast. Within decades, maybe even years, the climate could flip like a switch. In the 1990s, the Greenland Ice Core Project and the Greenland Ice Sheet Project 2 drilled even deeper cores. They found ice nearly 250,000 years old. The Antarctic cores went back further. The Vostok Core, completed in 1998, reached ice 420,000 years old. Later cores from Dome Sea and Antarctica went back 800,000 years. 8 ice ages, 8 warm periods, all recorded in the ice. The pattern was undeniable. Scientists could now see the details. Each ice age wasn't uniform. There were cold periods and slightly less cold periods, advances and retreats. The climate wobbled even during glacial times. And the warm periods, the interglacials, weren't all the same either. Some were warmer than others. Some lasted longer. Our current warm period, the Holocene, has been remarkably stable. Unusually stable compared to previous interglacials. The evidence was overwhelming. Ice ages happened. They happened regularly. They followed a pattern. And we were living in a warm period between them. But knowing that ice ages happened wasn't the same as knowing why. The discovery of the pattern just made the mystery deeper. What could cause such regular cycles? What force was powerful enough to freeze half the planet every 100,000 years? That question would take another set of discoveries to answer. And even then, the answer would be incomplete. Because the more scientists learned, the more complex the picture became. The ice ages weren't just about ice. They were about everything. The whole Earth system responding to some trigger. Some combination of triggers, all working together in ways that scientists are still figuring out. It's kind of perfect, actually. Learning about ice ages while you're trying to sleep. These massive, slow changes that happened over thousands of years. Nothing urgent. Nothing that requires you to stay alert. Just the Earth doing what it's always done. Freezing, thawing, freezing again. Let the pattern carry you. The rhythm of it. 100,000 years is a long time to wait between ice ages. You've got nothing but time right now. Chapter 2. The orbital cycles. Here's the thing about orbits. They're not perfect circles. Earth doesn't glide around the sun like a ball on a string. It wobbles, it tilts, it shifts, and these tiny changes, over thousands of years, add up to something massive. Ice ages. A Serbian scientist figured this out in the 1920s. His name was Milutin Milankovic. He was an engineer, a mathematician, a prisoner of war who did calculations in his head to stay sane. And he discovered something nobody else had seen. Earth's orbit changes, not randomly, in patterns. Predictable cycles that repeat over and over. And when these cycles line up just right, the planet freezes. 3 cycles, 3 different wobbles, each one operating on its own schedule. The first cycle is about the shape of Earth's orbit. Right now, our path around the sun is almost circular. Almost, but not quite. It's slightly oval, stretched out. This shape changes over time, sometimes more circular, sometimes more stretched. The cycle takes about 100,000 years. When the orbit is more circular, Earth stays about the same distance from the sun all year. When it's more oval, we swing closer in summer and farther away in winter. The difference isn't huge, but it matters. The second cycle is the tilt of Earth's axis. Right now, our planet leans at 23.5 degrees, like a top spinning at an angle. This tilt gives us seasons. When the northern hemisphere tilts toward the sun, it's summer there. When it tilts away, winter. But that angle changes. Over 41,000 years, Earth's tilt shifts between 22.1 and 24.5 degrees. More tilt means more extreme seasons. Hot summers, cold winters. Less tilt means milder seasons. Cooler summers, warmer winters. And here's what matters for ice ages. It's not about how cold winter gets. It's about how cool summer stays. Ice builds up in winter. That's normal. But if summer isn't warm enough to melt at all, the ice stays. Year after year, building, thickening, spreading. Less tilt means cooler summers, which means more ice survives, which means glaciers grow. The third cycle is the wobble of Earth's axis itself. Imagine a spinning top. As it slows down, it wobbles. Earth does the same thing. Our axis traces a slow circle in space. One complete wobble takes 26,000 years. This wobble changes which season happens when Earth is closest to the sun. Right now, we're closest in January, northern hemisphere winter. In 13,000 years, we'll be closest in July, northern hemisphere summer. This matters because it affects how extreme the seasons are. If you're closest to the sun during summer, that summer gets even hotter. If you're farthest away during winter, that winter gets even colder. 3 cycles, 3 wobbles, each one changing how much sunlight hits different parts of Earth at different times of year. Milankovic calculated all of this by hand, with tables and charts and endless equations. He figured out exactly how much sunlight reached Earth at different latitudes during different seasons over the past 600,000 years. And he found a pattern. Every 100,000 years, the cycles lined up. The orbit became more oval. The tilt decreased. The wobble put the northern hemisphere farthest from the sun during summer. All at once. Less sunlight in summer. Cooler temperatures. Ice that didn't melt. Glaciers that grew and grew and grew. He published his theory in 1920, then refined it in 1930, then wrote a whole book in 1941 called Canon of Insulation and the Ice Age Problem. Nobody paid attention. The scientific community ignored him. His math was too complex. His ideas too different. He was from Serbia, not a major research center. And World War II was happening. Nobody had time for theories about ancient ice. Milankovic died in 1958, still mostly unknown, his work gathering dust. Then in the 1970s, scientists started drilling those ice cores. Long cylinders of ice pulled from Antarctica and Greenland. Ice that had been building up for hundreds of thousands of years, layer after layer. each one a snapshot of Earth's ancient atmosphere. They could measure everything: temperature, carbon dioxide levels, dust in the air, pollen from plants, volcanic ash, all preserved in the ice like a frozen library. And they found cycles. The ice showed clear patterns: warm periods, cold periods, repeating over and over. And when they measured the timing, it matched Milankovitch's predictions. Almost perfectly. 100,000 years between major ice ages. 41,000-year cycles in the tilt. 26,000-year wobbles in the axis. All there in the ice. Undeniable. They also drilled cores from the ocean floor. Sediment that had been building up for millions of years. Each layer contained tiny shells from plankton. These shells recorded the temperature of the water when the plankton lived. Warmer water, different chemistry in the shells. Colder water, different chemistry again. Same patterns, same cycles, same timing. Milankovitch was right. 30 years after his death, the evidence proved it. But here's the strange part. The orbital changes don't actually change the total amount of sunlight Earth receives. Not really. The planet gets about the same energy from the sun, whether the orbit is circular or oval, whether the tilt is steep or shallow. What changes is where that sunlight goes, and when. More sunlight at the equator, less at the poles. More in summer, less in winter. The total stays the same, but the distribution shifts, and that's enough. That tiny redistribution of sunlight is enough to trigger an ice age. Think about it. The difference in sunlight between an ice age and a warm period is only about 0.1%. 0.1%. That's all it takes. Earth's climate is balanced on a knife edge. A tiny push one way starts the ice growing. A tiny push the other way melts it back. The orbital cycles provide those tiny pushes. Regular, predictable, inevitable. But there's something weird about the 100,000-year cycle. It's the strongest pattern in the ice core data, the most obvious rhythm. But it shouldn't be. The orbital eccentricity, the stretch of Earth's orbit, has the weakest effect on sunlight. Way weaker than the tilt cycle or the wobble cycle. Yet it dominates the ice age pattern. Scientists call this the 100,000-year problem. Why does the weakest cycle create the strongest effect? Nobody knows for sure. There are theories. Maybe the other cycles amplify it somehow. Maybe feedback loops kick in. Maybe ice sheets themselves create momentum that takes 100,000 years to build and break. Ice is heavy, really heavy. A mile-thick glacier weighs trillions of tons. That weight pushes down on the Earth's crust. The land actually sinks under the ice. When the ice melts, the land slowly rises back up, but it takes thousands of years. Maybe that delay matters. Maybe the ice builds up over 90,000 years. Slowly, gradually, getting thicker and heavier. Then something tips it over the edge. The ice collapses. Not all at once, but fast compared to how long it took to build. Within 10,000 years, it's gone. Then the cycle starts again. The Milankovitch cycles are still happening, right now. Earth is still wobbling, still tilting, still changing its orbit. The cycles never stop. Right now, we're in a warm period, an interglacial. The ice sheets have retreated to Greenland and Antarctica. Sea levels are high. The climate is relatively stable. But according to the cycles, we should be heading back toward cold, slowly. Over the next few thousand years, the wobbles should align again. Summer sunlight at high latitudes should decrease. Ice should start building up. Except it's not happening. Earth is warming. Fast. Faster than any natural cycle would predict. That's us. Human activity. Carbon dioxide from burning fossil fuels. Changing the atmosphere in ways that overwhelm the natural cycles. We've broken the pattern. For now. Whether that's good or bad depends on your perspective. Ice ages are hard to live through, but rapid warming creates its own problems. The Milankovic cycles are still there, still operating, still wobbling Earth's orbit and tilt and axis. But we've added a new factor, a new force, and nobody knows exactly how it will play out. Will we delay the next ice age? Cancel it entirely? Or just postpone it until the carbon dioxide levels drop again? Thousands of years from now? The math that Milankovic did by hand in the 1920s is still valid. The cycles are real. The patterns are clear. But we've added a variable he never considered. Human civilization. Industrial emissions. The ability to change our own planet's climate. The wobbles continue. Silent, slow, inevitable. Earth keeps tilting and spinning and circling the sun. The same cycles that have driven ice ages for millions of years. But now we're part of the equation too. And the next chapter of Earth's climate story is being written by both natural cycles and human choices. The ice remembers everything. Every wobble, every tilt, every shift in Earth's orbit, trapped in those frozen layers, waiting to tell its story to anyone who drills deep enough to listen. Chapter 3. The feedback loops. So how do wobbles in space actually create ice on Earth? It seems impossible. Earth tilts a bit more. The orbit stretches slightly. And suddenly, glaciers appear, miles thick, covering entire continents. The connection isn't obvious, but it's real. And it all comes down to one thing. Summer, not winter. That's the weird part. You'd think ice ages start because winters get colder. More snow falls. Temperatures drop. Ice builds up. But that's not how it works. Ice ages start because summers get cooler. Just a little bit cooler. Not enough to notice day to day, but enough that last winter's snow doesn't completely melt. Think about it. Snow falls every winter in Canada, in Alaska, in Northern Europe. Feet of it. But every summer, most of it melts. The cycle resets. Winter adds snow. Summer removes it. Balance. But what if summer can't finish the job? What if the temperature stays just cool enough that some snow survives? Not all of it, just patches. In valleys? On north-facing slopes. Places where the sun doesn't hit quite as hard. That leftover snow sits through the next winter. More snow falls on top. The old snow gets compressed, turns to ice, gets heavier, denser. Next summer comes, still a bit cooler than normal. More snow survives. More ice builds up, year after year, decade after decade, century after century. The ice grows. At first, it's just snowfields, then ice patches, then glaciers, small ones in the mountains. But they keep growing, spreading, flowing downhill like frozen rivers. And here's where it gets interesting. Ice changes everything around it. White surfaces reflect sunlight. Fresh snow reflects about 80% of the sun's energy back into space. Dark surfaces absorb it. Forests absorb about 90% of sunlight. Ocean water absorbs about 95%. So when ice covers the ground, less heat gets absorbed. The area stays cooler, which means more ice survives the next summer, which means more sunlight gets reflected, which means even cooler temperatures. It's a feedback loop. Ice creates conditions that make more ice. Scientists call this albedo feedback. Albedo just means reflectivity. High albedo equals more reflection. Low albedo equals more absorption. A forest-covered landscape has low albedo. Dark green trees soaking up sunlight. Warm ground. Snow melts quickly in spring. That same landscape covered in ice has high albedo. Bright white surface bouncing sunlight away. Cool ground. Snow barely melts at all. The Milankovic cycles don't create much cooling on their own. The change in sunlight is tiny, less than 1%. But they trigger the feedback loop. And the feedback loop does the heavy lifting. It starts in the far north, northern Canada, Scandinavia, Siberia. These places are already cold, already get snow every winter. They're right on the edge, just barely melting all their snow each summer. When the orbital cycles reduce summer sunlight by even a tiny amount, these places tip over. Snow starts accumulating. Ice begins growing. The ice spreads outward, south from the Arctic, down through Canada, across northern Europe, into Russia. Glaciers thousands of feet thick, moving, grinding, reshaping the land. And as the ice spreads, it reflects more sunlight, which cools more area, which allows more ice to form farther south. The feedback loop accelerates. But there's another feedback loop happening at the same time. In the ocean, cold water holds more dissolved gas than warm water. You can see this with soda. Cold soda has more fizz. Warm soda goes flat. Same principle with ocean water and carbon dioxide. As Earth cools, the ocean absorbs more CO2 from the atmosphere. Less CO2 in the air means less greenhouse effect. Less greenhouse effect means cooler temperatures, which means the ocean absorbs even more CO2. Another feedback loop, this one involving the whole planet's chemistry. Scientists can measure this in ice cores, tiny bubbles of ancient air trapped in Antarctic ice. Each bubble is a sample of Earth's atmosphere from thousands of years ago. During ice ages, CO2 levels drop to about 180 parts per million. During warm periods, they rise to about 280 parts per million. The pattern is clear. Less CO2 equals colder climate. More CO2 equals warmer climate. The Milankovitch cycles start the process, but the feedback loops amplify it, turn a tiny change in sunlight into a massive change in climate. It takes time, though. A lot of time. The ice doesn't appear overnight. It builds gradually over thousands of years. Each summer leaves a bit more snow. Each winter adds another layer. The ice sheet grows inch by inch, year by year. Imagine living through the start of an ice age. You wouldn't notice. Not in your lifetime. Maybe summers feel slightly cooler. Maybe snow lingers a bit longer in the mountains, but nothing dramatic. Nothing obvious. Your grandchildren might notice more. The snow line creeping lower. Glaciers in the mountains getting bigger. Winters lasting longer. 1,000 years later, the changes are undeniable. Glaciers have advanced miles. Forests have retreated. The climate has shifted. 5,000 years later, ice covers half the continent. Everything has changed. The ice builds fastest at the beginning, when it's small and only in the mountains. Then it slows down as it gets bigger. Spreading across flat land takes longer. The ice has to flow, push outward under its own weight. At its peak, the ice sheets are 2 miles thick in places. The weight is incredible. So heavy, it pushes the Earth's crust down. The land actually sinks, hundreds of feet under the ice. All that ice has to come from somewhere. From the ocean. Water evaporates from the sea. Falls as snow on the ice sheets. Gets locked up in glaciers. Doesn't return. Sea levels drop. During the last ice age, the ocean was 400 feet lower than today. Coastlines were completely different. Land bridges appeared. Britain connected to Europe. Alaska connected to Russia. You could walk between them. The ice keeps growing until something stops it. Until the feedback loops reverse. And here's the thing. The same orbital cycles that triggered the ice age eventually ended. Earth keeps wobbling. The tilt changes. The orbit shifts. After tens of thousands of years, the cycles swing the other way. Summer sunlight increases. Just a tiny bit. But enough. The ice starts melting at the edges. Slowly at first. Just the southern margins. But melting creates its own feedback loop. As ice melts, it exposes dark ground underneath. Dark ground absorbs more sunlight, which creates more warming, which melts more ice. The albedo feedback runs in reverse. The ocean warms up slightly, releases some of that dissolved CO2. More greenhouse gases in the atmosphere, more warming, more melting. The ice that took 90,000 years to build can collapse in 10,000 years, sometimes faster. The end of an ice age happens much quicker than the beginning. But here's what's strange. The orbital forcing, the push from the Milankovic cycles, is the same strength going into an ice age as coming out of it. The change in sunlight is symmetrical, equal but opposite. So why does the ice grow slowly but melt fast? Nobody knows for sure. Maybe it's the feedback loops. Maybe they're stronger in one direction. Maybe ice is easier to melt than to build. Maybe there's some threshold effect, some tipping point where everything accelerates. Or maybe it's about where the ice is. Ice at high latitudes, near the poles, is stable, cold year-round, hard to melt. But as ice spreads south, it reaches areas that are warmer, more vulnerable. When the climate shifts, the southern ice melts fast. And once it starts, the feedback loops take over. The whole system is non-linear. Small changes can have big effects. Thresholds matter. Timing matters. The way different cycles interact matters. This is why the 100,000-year cycle dominates, even though it has the weakest direct effect. It's not just about the sunlight. It's about how the system responds, how the feedback loops amplify the signal, how ice and ocean and atmosphere all interact. Earth's climate isn't a simple machine. It's not like turning a dial. It's more like a pinball game. You hit the ball and it bounces around, hitting different bumpers, changing direction, building momentum. Small differences in the initial hit create huge differences in where the ball ends up. The Milankovic cycles are the initial hit. The feedback loops are the bumpers. And ice ages are the result of the ball bouncing around the system for 100,000 years. We can see this in the data. The ice cores show it clearly. Climate doesn't change smoothly. It jumps, sudden shifts, rapid transitions, then long periods of stability. The ice builds gradually, slowly, steadily for 90,000 years. And suddenly, within a few thousand years, it's gone. The climate flips, temperatures jump, sea levels rise. The world transforms, and then it stays warm for 10,000 or 15,000 years. An interglacial period, like the one we're in now, stable, comfortable, easy to forget that ice ages are the normal state. Because they are. For the past million years, Earth has been in an ice age about 90% of the time. The warm periods are brief interruptions, pleasant breaks between long frozen epochs. We live in one of those breaks, the Holocene, the current interglacial. It started 11,700 years ago when the last ice age ended. And according to the orbital cycles, it should be ending soon. Geologically speaking, the wobbles should be lining up to start the next ice age. Summer sunlight at high latitudes should be decreasing. Snow should be accumulating. Ice should be building, but it's not. Because we've added something new to the system. Something the Milankovic cycles never accounted for. U.S. Human civilization, industrial emissions, carbon dioxide from burning coal and oil and gas. We've increased atmospheric CO2 from 280 parts per million to over 420 in just 200 years. That's faster than any natural cycle. Faster than the ocean can absorb it. Faster than plants can use it. We've overwhelmed the system, and we've broken the pattern. The orbital cycles are still there, still operating, but we've added so much greenhouse gas that the cooling effect doesn't matter. Earth is warming instead, fast. We've essentially canceled the next ice age. At least for now, at least for the next few thousand years. Maybe longer. Whether that's good or bad depends on your perspective. Ice ages are hard. Glaciers destroy everything in their path. Sea levels drop. Climate zones shift. Entire ecosystems collapse and rebuild. But rapid warming has its own problems. Different problems. Rising seas. Changing weather patterns. Species that can't adapt fast enough. The wobbles continue regardless. Silent, slow, patient. Earth keeps tilting and spinning. The cycles keep turning. The same forces that have driven climate for millions of years. But now there's a new force in the equation. Us. And nobody knows exactly how it will play out. How long our influence will last. What happens when the CO2 levels eventually drop again? Thousands of years from now. The ice remembers. Every wobble, every tilt, every shift. Recorded in frozen layers. A library of climate history stretching back 800,000 years. Maybe more. And it's still recording. Still building. Still waiting to tell its story to anyone who listens. Chapter 4. The Carbon Connection. Carbon dioxide. It sounds so simple. Just a gas in the air. But it's one of the most important players in this whole story. When we talk about the cycles of ice and warmth, about Earth freezing and thawing, carbon dioxide is always there in the background. Quiet, invisible, but powerful. Let's see how it really works. Not just the big picture, but the details. How do we know carbon dioxide acts as an amplifier for ice ages? What is the actual evidence? And why does it matter so much? First, think about what we actually see in the records. Ice cores from Antarctica and Greenland are like time machines. Scientists drill down more than 2 miles through the ice. Each layer is a year or two of snowfall pressed into a thin sheet. As the snow fell, it trapped tiny bubbles of air. Those bubbles are still there. Ancient air frozen for hundreds of thousands of years. When scientists pull out an ice core, they can actually measure the air from, say, 20,000 years ago. They look for carbon dioxide in those bubbles. Turns out there's a clear pattern. Every time the planet was cold, an ice age, the carbon dioxide in the air was low, about 180 parts per million. Every time the planet warmed up, the CO2 rose back up to about 280 parts per million. It's not just a coincidence. The rises and falls match up almost exactly with the timing of the ice ages. The coldest times always have the lowest CO2. The warmest times have the highest. The lines on the graph move together like two dancers locked in step. Now, here's where it gets interesting. The CO2 changes don't just follow the temperature. Sometimes the CO2 starts changing before the big warming kicks in. Sometimes it lags a bit, but the two are always linked. When CO2 increases, the planet warms. When it drops, the planet cools. It's a partnership. How do we know CO2 is actually causing the change and not just tagging along? That's a fair question. People used to argue about it, but now the evidence is strong. Think about how greenhouse gases work. Carbon dioxide isn't the only one, but it's the most important for these timescales. Sunlight hits the Earth. The surface absorbs the energy. Most of it is radiated back out as heat, as infrared light. Greenhouse gases like CO2 trap some of that heat. They let sunlight in, but slow the escape of warmth. It's like putting on a thin blanket. If there's more CO2 in the air, more heat stays in. If there's less, the planet loses heat faster. This isn't a theory. It's basic physics. We can measure it in the lab. We can see it on other planets too. Venus is hot, not because it's closer to the sun, but because its atmosphere is full of carbon dioxide. So when the ice cores show that CO2 drops during ice ages, it means Earth's blanket gets thinner. More heat escapes. The planet cools, and the ice sheets can grow. When CO2 rises, the blanket thickens. Earth holds on to more warmth. The ice sheets melt. But how much does CO2 really matter? Is it just a small helper, or is it a big amplifier? Here's what the numbers say. During an ice age, the difference in CO2 is about 100 parts per million. 180 in an ice age. 280 in a warm period. That 100 ppm change is enough to shift global temperatures by about 4 to 6 degrees Celsius. That's 7 to 11 degrees Fahrenheit. It's a big swing, enough to turn Canada into a frozen wasteland or a green forest. Enough to cover New York City in a mile of ice or fill it with trees and rivers. The fact that CO2 changes line up so closely with temperature is a big clue. But there's more. Scientists can compare the timing in detail. When the planet starts to warm at the end of an ice age, the first thing that happens is a small increase in sunlight at high northern latitudes. That's the orbital cycles at work. Not much extra energy, but just enough to start melting the edge of the ice. It's like starting a fire. The orbital cycles are the spark, but CO2 is the fuel. Once the fire is going, it burns hot and fast. Without that fuel, the spark wouldn't be enough. Scientists have tried to model this with computers. They take the orbital changes alone and ask the model what happens. The answer is clear. You get some warming, but not enough to explain the real record. Add in CO2 changes, and the model matches the ice core data almost perfectly. The temperature swings make sense. The timing works out. The evidence comes together. There's another way to see the power of CO2. Look at the numbers. The direct effect of changing CO2 from 180 to 280 ppm is about 2 degrees Celsius of warming, just from the greenhouse effect. But that's only half the story. When the planet warms, other feedbacks kick in. The ice melts. That changes the reflection of sunlight. More dark ground, more heat absorbed. The oceans warm up and release more CO2. The atmosphere holds more water vapor, which is another greenhouse gas. All these feedbacks add up. The total warming is about double what you'd expect from CO2 alone. So CO2 acts as both a driver and an amplifier. It starts the process and then helps push it further. The system feeds on itself. A little warming releases CO2, which causes more warming, which releases more CO2. The cycle continues until something stops it. But where does all this CO2 come from? And where does it go? That's where the ocean comes in. The ocean is the real giant in this story. It holds about 50 times more carbon than the air. Most of it is dissolved. Like sugar in tea, some of it is in the deep ocean, some near the surface. The balance between these places is always changing. But slowly, during ice ages, the oceans are colder. Cold water can hold more CO2, just like a cold soda holds more fizz. So when the planet cools, the oceans soak up more carbon from the air. The CO2 level in the atmosphere drops. That helps the planet cool even more. But when the planet starts to warm, the oceans warm too. Warm water can't hold as much CO2. The gas bubbles out, escapes to the air. The CO2 level rises. The planet warms further. This is another feedback loop. There are other ways carbon moves between air and sea. Tiny plankton in the ocean use CO2 to build their bodies. When they die, some of their remains sink to the bottom, taking carbon with them. Ocean currents stir the deep and surface waters, bringing up old carbon or sending new carbon down. The winds over the ocean can even change how much CO2 bubbles out. During ice ages, the ocean currents and winds are different. The whole system slows down. Less mixing means more CO2 stays trapped in the deep ocean. When the ice age ends, the system speeds up. The deep ocean releases its carbon. The air fills up with CO2 again. Scientists have looked for evidence of these changes. They've studied ocean sediments, layers of mud at the bottom of the sea. These layers hold tiny shells from plankton, and each shell has a record of the water's chemistry. By measuring the carbon in these shells, scientists can see when the deep ocean was storing more CO2 and when it was releasing it. The results match up with the ice core data. During the coldest parts of the ice ages, the shells show the deep ocean was full of CO2. The atmosphere was low in CO2. When the planet warmed, the deep ocean released its carbon, and the air filled up again. There are even clues from the land. During ice ages, giant dust storms swept across the continents. The ice sheets ground up rocks, making huge clouds of fine dust. Some of that dust blew out over the oceans, especially the Southern Ocean near Antarctica. This dust carried iron, which is a key nutrient for plankton. When the dust fell into the sea, the plankton bloomed. They pulled extra CO2 out of the air, helping to lower the atmospheric carbon even more. So carbon dioxide is pulled in many directions at once. The ocean, the land, the winds, the plankton. Each piece matters, but the overall pattern is clear. Cold times mean low CO2. Warm times mean high CO2, and the swings are big enough to change the whole climate. Some people wonder if the changes in CO2 are just a side effect. Maybe the warming causes the carbon to rise, not the other way around. But experiments and models say otherwise. If you fix CO2 at ice age levels, the planet stays cold, even if the sunlight increases. If you add CO2, the planet warms fast. Even if sunlight doesn't change much, the effect is real. And it's strong. You can even see it in the speed of the transitions. At the end of each ice age, the warming is fast. Just a few thousand years. That matches the speed of CO2 rising in the ice cores. When CO2 jumps up, the planet follows. The ice melts. The forests return. Animals and people expand into new lands. If CO2 didn't matter, the change would be slower. The small increase in sunlight from the orbital cycles isn't enough to explain the quick jump. But with CO2 rising, the planet has a booster, a turbo button. That's why the change can be so sudden. So the evidence for CO2 as an amplifier is strong. The ice cores show the timing. The ocean sediments show the storage and release. The models show the effect on temperature. The details match up, but there are still open questions. For example, why does CO2 drop so much during ice ages? Why does the system shift between storing carbon in the ocean and releasing it? What causes the deep ocean to lock up so much CO2 for tens of thousands of years, then suddenly let it go? Some scientists think it's all about the way the ocean circulates. During ice ages, the winds and currents change. The deep water gets more isolated from the surface. Less mixing means more carbon gets trapped. When the planet warms, the ice melts. The winds shift. The mixing increases. The deep ocean releases its carbon. Others point to the plankton. Maybe the giant dust storms during ice ages supercharged the plankton, letting them pull more CO2 out of the air. When the dust faded, the plankton slowed down, and the CO2 went back up. There's even a role for the land. During ice ages, forests shrink, deserts grow, soil carbon changes. All of these things move carbon from one place to another. But the biggest player is still the ocean. Scientists are still working out the details. They build better models. Look for new clues. Drill deeper ice cores. Collect more ocean mud. But the big picture is clear. CO2 is the main amplifier. It doesn't start the ice ages, but it makes them much more dramatic. It turns small changes in sunlight into giant changes in climate. It's the reason why the planet can swing from Sahara-like deserts to frozen tundra and back again. And the numbers are huge. During an ice age, about 10 million square miles of land are covered in ice. When the CO2 rises, most of that ice melts away. Sea levels rise by over 400 feet. Coastlines move. Rivers change course. Ecosystems shift overnight. At least in geological terms. We see the effect everywhere. In the fossils of plants and animals. In layers of pollen in lake beds. In ancient soils buried under old ice. The story is always the same. When CO2 is low, life retreats. When CO2 rises, life floods back in. That's why scientists pay so much attention to CO2. It might be invisible, but it's not silent. It leaves its mark on the whole planet. And once you start looking for it, you see it everywhere. Here's something else to think about. The amount of CO2 in the air during these cycles is tiny compared to all the carbon in the ocean and rocks. But even small changes in the air make a huge difference. The planet is sensitive. The climate system is balanced on a knife edge. It doesn't take much to tip it one way or the other. A slow shift in CO2, a small change in sunlight, a change in ocean currents. The feedbacks do the rest. And that's why the ice ages are so regular, but also unpredictable. The orbital cycles set the timing, but CO2 sets the volume. The music plays, but the loudness changes. Sometimes it's a whisper, sometimes a roar. We can even see the CO2 amplifier working today. Since the Industrial Revolution, humans have added about 140 parts per million of CO2 to the air. That's more than the difference between an ice age and a warm period. The result is a planet that's warming faster and at any time in the last 10,000 years. But that's another story. Right now, we're talking about the natural cycles, the way the planet has moved between ice and warmth for millions of years. The CO2 amplifier has always been there, sometimes quiet, sometimes loud, but always in the background. It's a reminder that the planet isn't just shaped by rocks or ice or sunlight. It's shaped by invisible things too. Tiny molecules in the air, bubbles trapped in ice, gases dissolved in the sea, all connected, all playing a part. When you look at the big picture, you see a system that's both fragile and strong. It can flip from one state to another, given the right nudge, but it always finds a new balance, a new rhythm. CO2 is part of that rhythm, not the only part, but one of the most important. It's the amplifier that turns small changes into big ones. The reason why the planet can change so much and so quickly. And the evidence is all around us. In the ice, in the ocean, in the land, in the stories told by ancient air and old mud and fossil forests. Chapter 5, The Ocean's Memory. But CO2 isn't the only amplifier. The oceans themselves play a huge role too. Their currents, their hidden heat, their deep secrets. And when they change, everything changes. The ocean is a world all its own. It's not just a big pool of water. It's layered, moving, always shifting in ways that are hard to see from the surface. If you could slice the ocean open, you'd see something like a giant sandwich. Warm water on top, colder water below, and the deepest layers far beneath that. Each layer holds different amounts of heat and carbon, and how those layers mix and move changes everything for the planet. Let's start with what's actually happening down there. The ocean isn't still. Currents flow across the surface, sometimes for thousands of miles. The Gulf Stream, for example, brings warm water from the Gulf of Mexico all the way across the Atlantic to Europe. That's why winters in London aren't nearly as cold as winters in Quebec, even though both places are about the same distance from the North Pole. Ocean currents carry heat. They act like conveyor belts, moving warmth from one part of the globe to another. But the real action is deeper down. Think about the great conveyor belt of the ocean. Scientists call it the thermaline circulation. That just means it's driven by temperature and salt. Here's how it works. In the far north, near Greenland, the surface water gets very cold. Sometimes it even freezes to form sea ice. When that happens, salt gets left behind in the water. This makes the water heavier and saltier, so it sinks. This cold, salty water then flows south along the bottom of the Atlantic, slipping beneath the warmer water above. At the same time, in the Southern Ocean near Antarctica, a similar thing happens. Cold, salty water sinks and spreads north along the ocean floor. It can take hundreds or even thousands of years for a drop of water to complete this loop around the globe. This slow, deep movement is how the ocean stores and releases heat. It also locks away carbon. When surface water sinks, it carries carbon with it, trapping it deep below. When deep water comes back up, it can let that carbon out again. So what's the evidence that this circulation matters for ice ages? Scientists have looked for clues in the mud at the bottom of the ocean. Every year, tiny shells, bits of dust, and other debris settle down to the seafloor. Over time, these layers build up, like pages in a diary. By drilling into the mud, scientists can pull up long cores, samples that give a record going back hundreds of thousands of years. Inside these cores are clues about the past. Some are chemical, like the amount of carbon in the shells of tiny plankton. Others are physical, like the size and shape of the shells, which can tell you about the temperature of the water when they lived. One of the best-known examples comes from the Atlantic Ocean. During the last ice age, the deep Atlantic was different from today. It was colder, and the water was more isolated from the surface. Scientists can tell because the chemical fingerprints in the shells show a buildup of carbon in the deep sea. Less carbon was making its way up to the surface and into the air. Why would this happen? During ice ages, the winds and currents shift. The ocean lid gets tighter, less mixing between surface and deep water. The conveyor belt slows down. Cold, salty water still sinks, but it doesn't pull as much surface water down with it. The deep ocean becomes a carbon trap. Then, as the planet starts to warm, the system wakes up. The currents get stronger. More mixing happens between the deep and the surface. Carbon that was locked away deep underwater starts to leak out, rising up and escaping to the air. That's one reason why CO2 rises as the ice age ends. It's not just the land or the air changing. It's the ocean releasing its stored carbon. Let's look at a real example. In the southern ocean around Antarctica, there's a special place where deep ocean water comes up to the surface. This is called upwelling. It's like a slow-motion fountain, bringing cold, carbon-rich water up from the bottom. Today, this upwelling brings nutrients that feed massive blooms of plankton. But during the ice ages, things were different. Evidence from seafloor cores shows that during the coldest times, there was less upwelling. The wind patterns changed, and the water didn't rise as much. That meant less carbon made its way from the deep to the surface, and less escaped to the air. But as the ice started to retreat, the winds shifted again. Upwelling increased, bringing more deep water and its trapped carbon up to the surface. More CO2 bubbled out and filled the air. The planet warmed even faster. This isn't just a guess. Scientists can see the timing in the mud. The types of plankton change. The chemistry in the shells shifts. The layers show a pulse of carbon coming out of the deep ocean, right when the planet is warming up. The match is almost perfect. Now let's talk about how heat moves in the ocean. The ocean holds far more heat than the air. In fact, the top 10 feet of the ocean holds as much heat as the entire atmosphere above it. When the ocean takes an extra heat, it doesn't warm up right away. It absorbs the energy, mixes it around, and slowly releases it over time. During ice ages, much of the ocean's heat is locked up at the surface, covered by thick ice in the far north and south. The deeper parts stay cold and dark. But as the ice melts, the sun can warm a bigger area. The surface heats up, and more of that warmth can mix down into the depths. This mixing isn't even. It depends on wind, storms, and how salty the water is. Sometimes a shift in wind patterns can push warm water down deeper, spreading heat through the ocean. Other times, the ocean can trap cold water under a layer of warm water, keeping the surface mild, even while the depths stay chilly. A good example comes from the North Atlantic. Today, when the Gulf Stream slows down, Europe can get cooler winters. If the whole conveyor belt system changed, it could shift the climate much more. During ice ages, evidence shows the conveyor belt was weaker. It trapped more cold water in the deep ocean and helped the ice sheets grow. Scientists have even found hints of sudden events, moments when the ocean currents changed quickly. In some ice cores and seafloor records, you can see signs of abrupt warming or cooling that happened over just a few decades. These climate jumps may have been caused by big changes in ocean circulation. For example, a sudden rush of fresh water from melting ice could have shut down the conveyor belt. That would have left heat building up in the tropics while the north stayed cold. Let's get concrete. Around 12,800 years ago, the world was warming up after the last ice age. But suddenly, the North Atlantic cooled sharply for about 1,200 years. This period is called the Younger Dryas. What happened? The evidence points to a large flood of fresh water pouring into the North Atlantic from melting ice sheets. This fresh water stopped the formation of cold, salty water that usually sinks and drives the conveyor. With the engine stalled, heat couldn't move north as easily. The result? Europe and parts of North America got much colder, almost like the Ice Age had returned. Then, just as suddenly, the system restarted. The conveyor belt picked up again. Warm water rushed north, and the planet finished thawing out. The whole world shifted into the warmer climate we've had ever since. The ocean isn't just a background player. It's the memory of the climate system. It stores heat for centuries, even millennia. It soaks up carbon and hides it away, only to let it out again when currents shift. The evidence for all this comes from many places. Ice cores, seafloor mud, the chemistry of tiny shells, and even the ancient coastlines that show where sea levels used to be. There's more. During ice ages, sea level drops by more than 400 feet because so much water is locked up in ice sheets. This exposes huge areas of the seafloor, changing the shape of the continents. The shallow seas disappear. The edges of the ocean move far out from where they are now. This affects the way heat moves around the planet too. The new coastlines change wind patterns, ocean currents, and the way the sun's energy is absorbed. When the ice melts and sea levels rise, the shallow seas flood back in. New currents form. The whole system gets a fresh start. The evidence shows that these changes in ocean shape and depth play a role in the start and end of ice ages. Let's not forget the role of life in the ocean. Tiny plankton float near the surface, using sunlight to grow. They take in carbon from the water. When they die, some sink to the deep ocean, carrying carbon with them. This is sometimes called the biological pump. During ice ages, there are signs that this pump ran faster. More plankton grew, more sank, and more carbon was locked away in the depths. How do we know? Scientists look at the types of fossils and the chemistry in their shells. They can tell when plankton blooms were bigger. These blooms are often helped by dust blowing off the land, carrying nutrients like iron into the sea. We talked about this before, but here's something new. The strength of the biological pump is tightly linked to ocean circulation. When the deep ocean is more isolated, the pump works harder because nutrients stay near the surface longer. But when the currents start moving again, deep water rises and brings up nutrients from below. The pump slows down, and more carbon escapes back to the air. It's a delicate balance. The ocean's life and its circulation are tied together. All of this matters because the ocean sets the pace of climate change. The air can warm up or cool down in only a few years, but the ocean takes centuries to fully respond. That's why the end of an ice age isn't just a smooth, steady thaw. Sometimes it's a stop-and-go process. Warm years, then sudden freezes, then back to warming again. The clues are everywhere if you know where to look. In the North Pacific, scientists found layers of mud that show sudden jumps in plankton growth, matching times when the ocean currents changed. In the Indian Ocean, cores show shifts in salt and temperature that line up with big changes in the ice sheets. Even in the deepest parts of the Atlantic, there are chemical traces that show when the deep water was filled with carbon and when it was released. The big picture is this. The ocean isn't just a passive water tank. It's an active player in Earth's climate. Its currents move heat and carbon around the globe. When those currents change, the whole climate can shift, sometimes very quickly. Let's step back for a second. Why does the ocean circulation change in the first place? The answer usually starts with small triggers, like changes in Earth's orbit, which shift where sunlight falls. That can start melting ice at the edges. The fresh water from melting ice pours into the sea, making the surface less salty. That can slow down the sinking of cold water, which slows the conveyor belt. Less heat moves north, and the ice grows back. Or if the system tips the other way, the conveyor speeds up, bringing warm water north, melting the ice, and raising temperatures. It's a system full of feedbacks. Each piece pulls on the others. If the conveyor slows, the north gets colder, ice grows, and the ocean stores more carbon. If it speeds up, the north warms, ice melts, and carbon is released. And here's something even stranger. Even small changes in the ocean can have big effects. A shift in wind over the Southern Ocean, for example, can change the amount of deep water that rises, which can add or remove a lot of carbon from the air. That, in turn, changes how much heat the planet holds. It's all connected. There's also evidence from coral reefs. Some ancient corals, buried in what are now dry islands, grew at times when sea level was higher. Others stopped growing when sea level fell during ice ages. By dating these corals, scientists can track how fast sea level changed and how quickly ice melted. The speed of these changes matches the timing of shifts in ocean currents and carbon release. The ocean story is written in all these places: mud, shells, coral, chemistry, ancient coastlines. Each one gives a piece of the puzzle. When you put them together, you see a giant system, always in motion, always changing. Another clue comes from the Arctic Ocean. During ice ages, the sea ice there was much thicker and lasted all year. That made it even harder for deep water to form and sink. When the ice melted, the conveyor could start again. The timing of these changes matches up with big jumps in CO2 and temperature seen in the ice cores. Let's not forget how the ocean connects the whole planet. Warm currents flow from the tropics to the poles. Cold currents return along the bottom. When the system is working, heat spreads across the globe. When it stalls, some places freeze while others bake. The ocean also acts as a buffer. When the air warms, the ocean soaks up some of that extra heat, slowing the warming on land. But there's a limit. If the ocean gets too warm, it can't absorb as much heat or carbon. Then climate changes can speed up. So all the evidence points in the same direction. The ocean's circulation, its great currents and deep mixing, controls how much heat and carbon the planet can hold. When those currents slow or stop, the planet cools and the ice grows. When they speed up, the planet warms and the ice melts. And the really wild part? These changes can happen quickly, at least in geological terms. Sometimes the climate flips in just a few decades. Sometimes it lingers in one state for thousands of years. But it's always the ocean, quietly working in the background, that makes these swings possible. You can think of the ocean as Earth's slow heartbeat. Each pulse sends heat and carbon around the world. When the rhythm changes, so does the climate. The ice ages are not just about cold air and frozen land. They're about deep water, hidden currents, and the way the ocean remembers. So when you look at the history of Earth freezing every 100,000 years, you see the ocean at the center. It's the giant player that sets the stage for everything else. The evidence is there, in the mud, in the shells, in the ice, in the rocks. All of it points to the same story. The ocean moves, and the world changes. And while CO2 is the amplifier, the ocean is the stage and the engine. It stores the heat. It locks up the carbon. It decides when to release both. And when it does, the planet can swing from deep freeze to warm green world and back again. All these pieces, ocean currents, deep water, heat, carbon, plankton, ice, work together. They make the system tick. Chapter 6. Living between ice ages. So what does all this mean for us? Why does it matter that Earth freezes and thaws every 100,000 years? Why spend all this time talking about ice cycles and deep time? Let's start with something simple. These cycles aren't just background noise. They've shaped every part of the world we know. If you look at a map, the mountains, rivers, and lakes, so many of them are leftovers from the last ice age. The big flat plains in North America and Europe, smoothed out by glaciers. The Great Lakes, carved by ice and then filled with meltwater. Even the soil in your backyard, if you live in the north, was scraped up and left behind by a moving wall of ice. It goes further. The places where people live today, the routes we take, even the foods we grow, they all trace back to these ancient rhythms. Crops like wheat and barley got their start after the last ice melted. The forests and grasslands you see are the result of thousands of years of slow warming. Even the animals that survived, from deer to rabbits to songbirds, are the ones that could handle these wild swings. But here's where it gets interesting. If you zoom out, you start to see how fragile this moment is. Human civilization, cities, writing, farming, the whole thing is a brand new experiment. Modern people have only been around for about 300,000 years. But for most of that time, life was tough. The world was cold, dry, and dangerous. People moved with the seasons, following herds, searching for places to survive. Sometimes whole groups disappeared when the ice pushed too far. We got lucky. The last 10,000 years have been unusually warm and stable. That's when people learned to farm. They built villages, then towns, then cities. Rivers stayed in their banks. The weather was predictable enough for crops to grow. This short window, just a blip on the timeline, gave us a chance to build everything we know. But the ice is never far away. There are clues everywhere. In Europe, you can find rocks called erratics that were carried hundreds of miles by glaciers. In Africa, old riverbeds show where water once flowed during wetter times. In South America, fossils of giant sloths are found in places that are now dry grassland. All these signs point to a world that's always shifting. Let's talk about people for a minute. Imagine being alive 20,000 years ago, near the end of the last ice age. The world would feel harsh and empty. Huge ice sheets would block the north. Mammoths and woolly rhinos would roam the cold plains. People would live in small groups, huddled around fires. Always on the move, food would be scarce. Winters could last for years. But these people were tough. They made tools from stone and bone. They learned to sew warm clothes from animal skins. They painted pictures deep inside caves, maybe as a way to make sense of the world, or just to leave a mark. When the ice finally melted, some groups moved north, following animals in fresh land. Others stayed in the south, learning new ways to live as the climate changed. Now look at us. Most people don't worry about the next ice age. We have houses, heaters, supermarkets, but the cycles are still running in the background. The same changes in Earth's orbit and tilt are still happening, slow as ever. If nothing else changed, another ice age would start in tens of thousands of years. But things are different now. Over the last 200 years, humans have started to change the atmosphere. We burn coal, oil, and gas. We cut down forests and build cities. All this adds carbon dioxide to the air, a gas that helps trap heat from the sun. This is new, It's something the planet hasn't seen before, at least not this fast. Scientists are now asking a big question. Will the next ice age ever come? Or have we changed the rules? Some studies show that the extra carbon dioxide we've added could push the next ice age far into the future. Maybe tens of thousands. Maybe even hundreds of thousands of years. Nobody can say for sure. Think about that for a second. For millions of years, the world has flipped between cold and warm. But now, because of us, that pattern might be broken. We've become part of the story, not just as passengers, but as drivers. This brings up another point. Earth's climate isn't just about numbers and cycles. It's about life. Every time the world shifts, animals and plants have to move, adapt, or die out. When the ice comes, forests shrink and grasslands spread. When it melts, trees grow back and new animals appear. These changes can be slow or fast, but they always leave a mark. Sometimes whole groups vanish. The big animals from the Ice Age, mammoths, saber-toothed cats, giant ground sloths, are all gone now. Some disappeared when the world warmed up. Others may have run into trouble when people arrived, hunting them or taking over their land. Every cycle leaves winners and losers. People are good at adapting. We learned to fish, farm, and build. We crossed land bridges and sailed the seas. But even for us, big changes are hard. When climates shift quickly, there's less time to adjust. Crops might fail. Rivers could dry up or flood. New diseases can spread as animals and insects move to new places. It's a reminder that we don't control everything. The planet is huge and complicated. Even small pushes, like a shift in sunlight or a change in carbon dioxide, can tip the balance. Sometimes all it takes is a little nudge to set off a big chain reaction. Here's something humbling. Fossils show that life has survived much worse. There were times when almost everything died out, like the mass extinctions that wiped out the dinosaurs, or the snowball Earth events when ice may have covered nearly the whole planet. Somehow life bounced back. New forms appeared. The world kept spinning. But every time, the survivors had to start over. The rules changed. What worked before didn't always work again. It's a pattern that repeats, but never in exactly the same way. So where does that leave us? We live in a world shaped by chance, cycles, and choices. We're here because of a long chain of events. Some we understand, some still a mystery. The ground beneath our feet, the air we breathe, even the weather outside, all shaped by forces we can't see. Some people find this scary, others find it comforting. There's a kind of peace in knowing that change is normal, that nothing lasts forever. The world is always moving. The ice will come and go. Warm times will return. Life will find a way, even if it looks different each time. Here's another way to think about it. History isn't just about people, kings, wars. It's also about the land, the sky, and the deep rhythms of nature. If you go far enough back, you see that people are just one part of a much bigger story. The story of a planet that spins, tilts, and dances through space, always changing, always surprising. This doesn't mean we're powerless. We still make choices every day. The way we live, the things we build, the care we show for the land and water, all of it matters. We can't stop the cycles, but we can learn from them. We can try to be ready when things shift. We can pay attention to the clues the past has left for us. Think about how far we've come. From small bands of people hunting in the cold to cities that glow at night. From simple tools to rockets that leave the planet. All of this happened in a blink compared to deep time. It's easy to forget how new it all is. Sometimes it helps to slow down and listen. To see the world not just as it is, but as part of a long unfolding story. The wind in the trees, the shape of the hills, the path of a river. All of these are echoes of ice and fire, of warm times and cold. Next time you look at a map or walk down a city street, remember that the ground you stand on has changed many times before. Forests have grown and vanished. Rivers have shifted. Ice has come and gone. The world you know is just one chapter in a much longer book. So what's the lesson? Maybe it's that nothing stays the same forever. Maybe it's that we're lucky to be here right now, in this rare, warm window. Maybe it's that the story isn't finished. These cycles will keep rolling, with or without us. But for now, we get to be part of it. And in the end, that might be the most amazing thing of all. Out of all the possible worlds, we're here, living on a planet that freezes, thaws, and spins through space, watching the patterns, wondering what comes next, trying to make sense of our place in it all. If nothing else, the Ice Age cycles remind us to stay curious, to look for clues, ask questions, and never take the present for granted. The world is full of surprises, both big and small. Every day we walk through the results of ancient changes. Some we notice, most we don't. The next ice age may be far away, or maybe it won't come at all, thanks to what people have done. Either way, the story of Earth is still being written. And for now, we get to watch, learn, and wonder. So as you drift off, let your mind wander through deep time. Imagine the glaciers growing and shrinking, forests spreading, rivers carving new paths. Picture the world changing, slow and steady, always moving forward. You're part of that story too. A tiny piece of a planet that never stands still. Rest easy, knowing that change is the only constant. The ice will return. Or maybe it won't, but the story goes on. And you, for this moment, are right in the middle of it. The 100,000-year cycle continues, silent, patient, indifferent to our confusion. Earth keeps wobbling, keeps tilting, keeps moving through space. The ice keeps recording, keeps building, keeps waiting, and we're here, between ice ages, in this brief window of warmth, this moment of stability, this rare chance to build and grow and wonder. The pattern carries on. The rhythm never stops. 100,000 years is a long time to wait between ice ages. But the planet has nothing but time. And for now, so do you. Let the cycles carry you. The slow rhythm of Earth breathing in and out, freezing and thawing, ice and warmth, over and over, for millions of years before us, and millions of years to come. Rest now. The ice remembers everything, and the story continues, always.